Our next talk is online. It's by Treu from UCLA. And Tommaso will tell us about dark matter and cosmology from strong lenses in the age of Roman.
Good morning. So quasars and supernovae that are multiply imaged by a foreground galaxy or cluster of galaxies, I will show you, provide unique and incredible insights into the fundamental constituents of the universe. They can tell us what the universe is made of, from the nature of dark matter to the expansion history of the universe and the nature of dark energy. However, up until now, these phenomena are extremely rare. Very few of each category are known to date. What Roman will do is will revolutionize the field by making these phenomena increasingly abundant. We will have hundreds, if not thousands, of each one of these things. And by the sheer power of Roman, we will be able to finally answer some of the most pressing questions in cosmology. So let me take you to a brief history and prospects of cosmography and cosmology with strong gravitational lenses. I'll give first a brief introduction about the expansion history of the universe and the nature of dark energy, and talk about the nature of dark matter. Then I'll talk about how strong lensing can constrain the expansion history of the universe and therefore dark energy, and then how the abundance of dark matter on very small scales is a probe of the nature of dark matter itself, the particle nature of dark matter. And I will conclude by explaining how Roman will revolutionize the field by making lenses not rare anymore. And also one of the things that is unique of Roman is that in many cases, Roman will not only provide the discovery images or discovery spectra of these systems, but also crucial follow-up data. So let me start. This is a very simple picture. I'm sure many of you have seen this before. The standard cosmological model consists of a universe where 95% of the energy budget is made of dark matter and dark energy. And dark matter is something called cold dark matter, a massive non-relativistic, non-interacting particle gives rise to the hierarchical structure that we're used to seeing in simulations. There are two problems with this picture. The first one is that we don't know what dark energy and dark matter actually are. So we know they're most of the energy of the universe, but we don't know what their fundamental nature is. And the second problem is that this may not be correct. So let me get to the second part of it. Recently, some cracks seem to have opened in our understanding of the expansion history of the universe. One of them, perhaps the most interesting, is the so-called Hubble tension. So if you measure the expansion history of the universe today, the Hubble constant, the expansion rate of the universe today, you obtain a certain number. And if you measure some properties of the early universe, say at the time of recombination, at the time of the CMB or Big Bang nucleosynthesis, and extrapolate what those parameters would predict for the expansion rate today, sometimes you find that they do not match. So the so-called early probes of the expansion history and the late probes of the expansion histories don't seem to match under the assumption of the standard cosmological model. So this is a recent paper summarizing the state of the tension. You can see that there are measurements from the early universe that seem to prefer a relatively low value of the Hubble constant, and most measurements from the late universe seem to prefer a higher value of the Hubble constant. You can read this Abdallah paper, which is a much larger number of measurements. Of course, there are uncertainties in all these measurements, but this seems to be a pretty strong tension. How do we solve the tension? Well, it's not easy. So one of the ways that it was thought promising to solve this tension was to increase the expansion rate just before recombination. So if you modify the expansion history of the universe before the acoustic scale of the CMB and the baryonic oscillations is set, then you can reconcile the two measurements. But this requires, for example, new relativistic particle, or even perhaps a new form of dark energy called early dark energy. So you would have a third phase of accelerated expansion of the universe in between inflation and the dark energy we all know and love, a few billion years, that takes over a few billion years ago. There are problems, however, with all of these solutions. So this is a paper with a catchy title that summarizes why it's not easy to solve the Hubble tension from a theoretical standpoint. And the recent discovery by DESI, or the recent measurement by DESI, that dark energy may not be the cosmological constant, makes it even more complicated. There's a flurry of activity of trying to reconcile the Hubble tension with DESI. There may be ways to do it, maybe modifying recombination physics. It's certainly very complicated, but it's also potentially very interesting because, as someone told me once, the most interesting sentence in physics is not eureka, but something's funny here. So there's a possibility that this may be the beginning of an important discovery. And the other aspect is, of course, what is dark matter? So we've known for many years now that the gravity field of galaxies and clusters and so on are dominated by something that is a non-baryonic particle, non-interacting with light, or maybe more than one, but we don't know what it is. So if you ask a theorist, a particle physics theorist, there's hundreds of possible models of what this dark matter could be. And this is a nice diagram from Tim Tate that tries to classify all the possible explanations, ranging from supersymmetry to extra dimensions, sterile neutrinos, you name it, whatever your favorite flavor is. If you ask an observer, this is what we see. So we only see the light that comes from galaxies. We cannot see the dark matter itself. So there we have a problem. One way to try to connect the two is to use cosmological simulations. And this is a nice example showing a universe simulated on one side in cold dark matter, the standard WIMP, weakly interactive massive particle. On the other side, the same simulation carried out with a sort of KV scale thermal relic or some sort of sterile neutrino that keeps the structure on large scale the same, so not violating all the cosmological constraints, but changes dramatically the number of very small structures. Okay, so how does strong lensing help with this? In two ways. One is time delay cosmography. So if you have a source that is variable in time, like a supernova, the supernova here goes off, emits two rays, ray A and B. The light paths are bent by a foreground cluster or galaxy, and the two rays reach the observer, forming two images, but ray A gets there first, and ray B gets there later. The difference in arrival time can be measured with a clock, and so it's an absolute measurement. We know the speed of light, so we can determine this distance, and it's simple trigonometry to go from this distance to the distance to the deflector and the source. And this is the essence of time delay cosmography. You measure distances basically with a clock by measuring the difference of arrival time of photons. In practice, the difference in arrival time is proportional to a distance called the time delay distance. And like every distance, that is proportional, inversely proportional to the Hubble constant and sensitive also to other parameters like the amount of dark matter, the equational state of dark energy, and so on and so forth. In practice, you have to measure the difference in arrival time. You have to measure and model the gravitational potential of the foreground deflector. Then you infer the time delay distance and finally convert it into cosmological parameters. So this took some time to figure out. It was proposed more than 50 years ago, but finally we think we know how to do it. So we need to measure time delays, do very precise astrometry. So we need high resolution. We need to model the lenses. And finally, we need to account for everything along the line of sight, which we do through numerical simulations. Okay, so one important thing in all of this is that these are very difficult measurements. So I think it's important to do them blindly so that you don't run into what is called experimental bias. And so many of the measurements that I will show you now today are blind. So we don't know the answer until we finish the measurement, and we are blind only prior to measurement. So this was the state of time delay cosmography in about early 2020. On the left, you see the early universe probes. On the right, you see the time delay cosmography measurement in combination with SHOES, the method that uses Cepheids and supernova to determine the local value of the Hubble constant. And there was a strong tension between these two sets of independent measurements and the two sets of independent measurements from the early universe. Now, of course, this is an extraordinary claim because it requires that standard cold dark matter is broken. And so we think, following Sagan, extraordinary claims require extraordinary evidence. So we went back through all this measurement and tried to address a number of potential systematic uncertainties. One that really pops up is the assumptions about the mass density profile of the deflector, in this case, galaxies. So when you're measuring galaxies, what we've been doing until 2020 was using a power law or stars plus a standard dark matter profile. And this is the way that elliptical galaxies have been described successfully for decades. This is the standard assumption. If you do that, you end up with a measurement of the Hubble constant that is about 74 or so on and so forth. But there's one way in which you can be more conservative. And in lensing, there's something called the mass sheet degeneracy, which is a rescaling, a mathematical rescaling of the surface mass density of the deflector in a way that preserves the image positions. So some of the solutions, of course, will be unphysical, so you have to eliminate those. But this maximizes the uncertainty of the Hubble constant. So this is the most conservative measurement way you can do to estimate the uncertainties on this method. And so if you do this, of course, uncertainties increase, and you don't change very much the mean value of the measurement, but the uncertainty goes from about 2% to about 8–9%. And so we now are in a position where if we want to recover the 1% measurement of H0, which I think is needed to clarify this issue of the expansion history of the universe, with no assumption in the mass profile, you need to do something differently. So what you need to do is you need to have many more systems. And this is where the Roman Space Telescope really shines, because you need to have much larger numbers of lens QSO supernovae. The measurement I showed you before, it was based on just 7 because they're so rare. And also get better precision per system, which can be done, for example, with resolved stellar kinematics of time delay lenses. This is not something that Roman can do, but can be done on systems discovered by Roman. So going to the other topic, the nature of dark matter itself. The key to understanding the nature of dark matter is to study the distribution of mass on very, very small scales. When I say small scales, I mean subgalactic scales comparable to the lower mass satellites of the Milky Way, something like 10 to the 7 solar masses, halos surrounding brighter galaxies. And why is that so important? This is so important because in cold dark matter, the number of subhalos as a function of mass is a pure power law. The number of subhalos goes as mass to the -2. And so you expect, if you count subhalos, you expect to find more and more as you go to lower and lower masses. In alternative models, like for example, warm dark matter, like a stellar neutrino, you expect a turnover in mass function because due to free streaming, subhalos would not just form below a certain mass. And so you expect a turnover here in the mass function. Interestingly, we know that this turnover has to be probably below some 10 to the 7 point something solar masses. And that's critical because below those masses, subhalos potential wells are not sufficiently deep to retain gas and form stars. So all the subhalos that you see down here at the low end of the mass function are virtually dark. So cold dark matter predicts that there should be thousands, if not tens of thousands, of balls of dark matter flying around every galaxy. But we cannot see them because they cannot form stars. Now, with strong lensing, of course, you can see them because strong lensing is sensitive to mass, not to light. And so strong lensing can detect satellites based solely on mass. And the way normally satellites are detected as anomalies with respect to smooth distributions of mass. So if the gravitational potential maps directly into lensing observables, the second derivatives of the potential regulate the ratio of brightness of the images. The first derivative regulates the position of the images, and the potential itself regulates the time delay. And the natural scale of the problem here is a few milliarc seconds because astrometric anomalies are expected to be over the 10 milliarc second. So you really need something with Hubble or Raman-like resolution to study these things. And just to bring this home, these are Hubble images of lenses. And you see, for example, these two images here that on the left that are next to each other, they should have the same brightness if the mass distribution within the reflector were completely smooth. Instead, one is 100 times brighter than the other, pointing to the existence probably of a dark satellite some in front of this fainter image, and so on and so forth. The problem is that if you're just looking at images, you don't know if this is due to dark satellites or if it's due to astrophysical noise. For example, you could have a dust rain, or you could have microlensing by stars creating this effect. So you need to look at flux ratios at wavelengths that are not affected by these things. And so you need larger samples, and this is what Raman will do. And you need to do high precision photometry and astrometry. Raman will do that. And also you need to avoid microlensing. And to do that, you need to look at something like the narrow emission lines, like O3 or O2, that come from the narrow line region, which is too large to be microlensed, or dusty tori. This is what, for example, is done with GWST. Okay, so this is an example of one of these studies done with Hubble. You can see this is a quasar that is lensed by a foreground galaxy producing 4 images, and you can see the Hubble grism on board with C3 disperses the light, and then you can use the spectra to measure O3, indicated here by the blue arrow, and measure the flux ratios in the emission line. Now, of course, this was hard work with Hubble, partly due to the relatively low spectral resolution of the spectrograph on board of Hubble. With Raman will be easier because it will have higher spectral resolution. And of course, with Hubble, we could do it only for a handful of objects. With Raman, we'll do it for much larger samples of objects. And so today, the state of the art here is that this turnover mass, the mass at which the subhalo mass function turns over, is less than 10 to the 7.6 solar masses. So we are approaching the limit where we should be able to detect, to prove the existence of these balls of dark matter floating around galaxies. And in terms of a thermal relic, the mass of the thermal relic has to be larger than 6.1 keV. Now, the limits for stereo neutrino will be different, but you can apply this method to any dark matter theory you have, from mixed dark matter to self-interacting to primordial black holes, whatever you want, you can apply this method to. And so the future prospects are great. So as you can see, as you increase the number of lenses, at the moment we have about 30, and you increase the precision of the fluxes, which we'll be able to do with Raman, the limits on, say, in this case, the mass of the thermal relic becomes, lower and lower and lower in this diagram, which means the mass of the particle becomes larger and larger and larger. As it becomes larger, you approach the limit where it's indistinguishable from cold dark matter. And you can consider other models, for example, self-interacting dark matter. In this case, the dark matter interacts with itself with a velocity-dependent cross-section. And you can also constrain this. But you need a large number of lenses. In this case, for example, you need 50 or more. And we just don't have them now, but we will have them with Raman. And so since I'm calling in from Rome, I want to talk about the Roman Revolution. This one, where Julius Caesar was killed by his rivals, but not this one. Let's focus on the Roman Revolution, the revolution of the Roman Space Telescope. With Roman Space Telescope, the strong lenses will not be rare anymore. So there are approximately 0.1 lens per square degree lens quasar at the depth of the high latitude survey. So there would be about 200 for 2000 square degrees. Well, I would guess a little more just because the resolution is so good and the performance is so good. But this is at least an order of magnitude improvement to what we have now, and there will be all the other surveys, so we can imagine the number will be larger. Strongly lensed supernova will not be rare anymore. This is a nice study by Justin Pirro showing the expectation for the number of core collapse and 1A supernovae to be discovered by a number of different surveys, planned or potential surveys to be carried out with Roman. For example, the high latitude survey will discover hundreds of such lens supernova. And there's an idea floated here of an ultra deep survey, which will not only discover a lot of supernova, but also be able to get their time delays. And one of the things that is really striking of Roman, I would say, is that it can, hold on, it can not only discover lenses, but also measure, provide you a mass model. So this is a comparison of lenses, the same lenses observed with Hubble, Keck, AO, JWST, TMT, IRIS, and 3 surveys from the top: Rubin, Euclid, and Roman. As you can see, Roman is the only one in this case that has sufficient resolution and sensitivity to detect the Einstein ring, the extended host galaxy of the quasar, which is really what we need to model the gravitational potential of the deflector. So one of the main bottlenecks of studying strong lenses is to do the high resolution follow-up. With Roman, for many of the lenses, the survey itself will provide the high resolution images that are needed to exploit it for cosmology. The time delay also, so according to Peter et al., some survey strategies with Roman can deliver time delays for, say, 10 or 20 supernova. For larger numbers of supernova, there would be the need for dedicated follow-up, and this can be done either from the ground, using Roman images as templates to deconvolve the lower resolution images, or maybe in some overlapping areas with Rubin. Rubin will provide the time delays, or maybe you'll need some other effort to do the time delays. This is, I think, something that needs to be carefully planned. And another ingredient that is needed is redshift and kinematics, redshift of the lens and source. Some of it can already be obtained by Roman with the GRISM. Some will require ground-based spectroscopy, probably for the redshift 8 to 10 meter class telescope will be sufficient. For time delay cosmography, when the source is not a 1A, we need stellar kinematics to break the mass sheet degeneracy. And that will require probably JWST, Keck, for the brighter systems. And for a really large sample, I think we'll need the extremely large telescopes, such as TMT or equivalents. Unresolved kinematics, so not spatial resolved, can be done probably with 8 to 10 meter class telescopes, but then the mass sheet anisotropy degeneracy is more a concern there. So I think there will need to be some effort will need to be put into doing the follow-up, but Roman will definitely provide a great start with the discovery, redshifts, and some information on other things. For flux ratios, the fantastic thing about Roman is that for some systems with suitable redshifts, Roman will provide the line ratios. We will be able to measure narrow line emission ratios from survey data itself. And for other systems, one can work and do follow-up, either with advanced adaptive optic systems, probably, or from JWST. And just to whet your appetite about what time delay cosmography can do, so these are forecasts in WCDM, so this is CDM with free equation of state of dark energy, showing the power of lens supernovae in red. And if you do an ultra deep survey, you can see how tight the constraints get. But more interestingly, it shows the orthogonality of the lens supernova constraints with respect to the supernova CMB and BAO, showing the great synergy between these methods. And so I think this has tremendous power. Some of it, of course, will require follow-up of Roman discoveries, but I think it's well worth the effort. So to summarize, the Hubble tension and the DESI measurements may indicate a major departure from lambda CDM. Given the stakes, I think it's crucial to obtain multiple independent measurements of the expansion history of the universe, and gravitational time delays are a powerful one-step method that can reach 1% precision with resolved kinematics and the large samples provided by Roman. And this is, of course, independent of all other methods. The nature of dark matter is unknown, many alternatives to CDM are viable from a theoretical standpoint. And lensing is probably one of the few probes that can test departures from CDM on the scales that are needed, because at the scales that we're reaching now, these departures will manifest themselves in systems that are devoid of stars and therefore do not have much electromagnetic interaction. And in principle, any theory of dark matter that has observable consequences on those scales can be tested using strong lenses. So I think there's ample scope here to learn something about the fundamental nature of dark matter. And I will conclude here.
Thanks, Tommaso. Perfect timing. I was just about to give you the 1-minute warning when you reached your summary slide. So do we have any questions either in the room or online?
Hey, Tommaso. So for the 200 or so lensed quasars that could be in the high latitude survey, is the spectroscopy for the sort of reference mission plan deep enough, or would you have to go back and go get much deeper grism spectroscopy for the multiple components, or for the flux variations, or would it sort of just drop out of the survey?
I think that it will be a combination. So for many of the systems, the spectroscopy will probably be good enough to get a redshift already. So that's great. For the flux ratios, I think it will depend, of course, on how bright are the emission lines. So if they're bright enough, you'll get them. But to give you an idea, with Hubble, we've been able to do a lot of them, and it was much harder with Hubble because the resolution was lower. So I'm pretty confident that for many of the systems, we will get the flux ratios from the survey data itself. Now, of course, in some cases, depending on the configurations, they will overlap. We will not be able to deblend them and so on and so forth. So the success rate would not be 100%. But even if it were, say, 50 or 30%, you're still doing great because the current samples are like 10 or 20. And if you have half of 200 is a much larger number.
Other questions? I actually have one. So at the beginning of your talk, you showed the plot with the different comparisons of the probes with the constraints on H naught. And you might have said this, but so given Roman's like the samples that we expect from Roman, what would this plot look like in terms of the early versus late? Would we have a very clear picture here?
I think so. I think that we will see the error bars here for some of the methods are 8, 9%, or 6 or 7 at the top here. And you will get all of them down to 1% or 2%. And that's just to give you a sense, the difference between the shoes and the Planck measurement is about 8%. So if you have a measurement that is between 1 and 2% precision, you can distinguish them at 5 sigma. So I think we will have multiple probes that have the precision and hopefully accuracy to distinguish the Planck and shoes measurement at 5 sigma.
Mm-hmm. Okay.
So it will be much clearer. Imagine this plot, hopefully with error bars that are all as small as the Planck and BBN points at the bottom, and hopefully not all over the place, but clustered either on the left or on the right or on the middle. It's clustered somewhere, let's say. Yeah.
Yeah. All right. Any last questions? If not, let's thank Tommaso again.
Thank you, guys.